Okay. Um, I should be kind of going through and grading those individual assignments tonight and tomorrow. I have them done at some point tomorrow. Also tomorrow I'll post a link with some more details about the final, kind of a question breakdown, multiple choice versus short answer. I already told you I think the length, which will be 2 hours, but I'll get like an announcement up with all the information about the final tomorrow. Other than that, once I get those 30 individual assignments graded, I will go through and determine your lowest of each homework type, kind of drop it, and kind of structure Canvas a little bit. And I'll talk about it Friday, how to kind of look at, and you'll probably be able to figure it out, but just in case you can't, how you take on Canvas and apply it to that, figure out your grade tool. Other than that, are there any questions for me before we kind of jump into things here? Okay, so we've got final exam. This is not what I want. Oh, maybe this is what I want. Is this what we did last class? I think this is for my regular section. The wrong file open. Hold on, my bad. Practice exam. Here we go. So we worked through quite a few of these. Some of the older stuff. I believe we worked through the SAT. Kept going. One thing that we didn't do is kind of this set of questions. So I'll kind of start on 11, unless there's like specific questions that you want to go through. But I think we should have a chance to get through 11 through 13. And then I'll probably move to, where is it? Right here, kind of 17, and kind of move through the rest of those as well. And correct me if I'm wrong, I'm starting to get things mixed up between the two classes, but I believe we did the GPA SAT score variable. I don't believe we did anything with the birth weights last class. Is that, anyone want to confirm that for me? Because I don't want to go through this. Okay, I don't want to go through the same thing again, but so we'll start with 11. So let's say we want to estimate the relationship between a child's birth weight and a mother's age, where the birth weight is the dependent variable. We obtain data for 1,600 some births, and we have the following kind of questions. So first thing here isn't a question that's up here, but suppose I had a question where I just kind of asked, write out the regression equation, right? So here we've got birth weight as our dependent variable, and we want to try to explain it using the mother's age. So really what we're thinking about, if I can spell right, is birth weight being a function of mother's age, okay? So let's say we get an intercept coefficient that is 3,524. So what we're thinking about here is, once we actually obtain those estimates, make this an equation so that I can put a little, all right, we're trying to predict birth weight. We get that the intercept is 3,524. I don't give you kind of the slope coefficient yet, but eventually we'll kind of be able to plug that in. So it doesn't matter what that slope coefficient is. We're interpreting the intercept. What we're saying is if all x variables are equal to 0, or we only have one x variable here, so if we were to plug in 0 for that, notice 0 times anything would be 0. So the interpretation of the intercept is that if every variable is equal to 0, the predicted value for our y variable birth weight would be whatever that estimate was, which was about 3,500. So the expected birth weight for a mother who is 0 would be 3,524. That's kind of our interpretation of that intercept. It was a little bit easier here because we only had one variable on the right-hand side, but more generally, the interpretation is every x variable is equal to 0. The predicted value of y would be whatever that intercept coefficient was, okay? Won't spend too much time on 12, but it's one of these questions where let's say that we did come up with a slope coefficient and the test statistic was 2.54, right? And translated to a p-value that was pretty low. Well, let's just make up some value. I don't know. Let's say this is, 3.5. So what that would be telling me is that as a mother, every additional year that we see the mother's age, the predicted birth weight of the child goes up by 3.5. And I believe it's like all these examples we've been looking at. As a reminder, we've been measuring birth weight in grams. Okay? So what we have to remember is that just because a mother gets older, saying the child will have a higher birth weight, well, there's a correlation between those two things. But it could be that we're leaving something important out. So we want to make sure that we remember this regression is only evidence of a correlation. It could be that as the mother gets older, she also has more education, more income, all these other things that might be positively correlated with birth weight. But if we don't include those as control variables on the right-hand side, our coefficient will pick up the effect of all those things as well. So if we look at that formula sheet, right, I'll zoom in here for us. If we remember, if we left out important variables, call it x2, then when we get this estimate for the slope coefficient, it's going to contain the true relationship between that x variable, x1 we included in y, but also this additional bias component, right? So it's just evidence of a correlation. It could be that there's other important omitted variables that we're picking up a bias from, okay? So what could be one omitted variable other than this education that I mentioned that might be kind of affecting this coefficient on mother's age? And which direction do you think it would affect the bias? So here, I think the one that I mentioned was income, right? So let's think about income as our x2 variable, okay? So income is this variable that we left out. We kind of think about it as mother's age was the variable that we included, or our x1 variable. Okay. So if I think about that bias that exists in my estimate, right? So here's my estimate that I can observe. That would be like, let's say I had the regression output and I saw that it was 3.5, okay? So I think about that coefficient estimate I have is 3.5, but that will include the true effect, right? The true kind of relationship, but also this additional bias component. So what we're going to try to do is we're going to try to put a sign to say, is this a positive bias, a negative bias, and how can we do that? So we go back to the problem. I'm just going to copy and paste what that bias is, right? So here, beta 2 would be the relationship between that variable that I left out and my y variable of birth weight if I had included that variable in the regression. So if I had included the mother's income, what would you expect the sign of this coefficient to be? Now this is one of those, there's no right or wrong answer, right? As long as you give me the assumption about y, then that's okay. So I'm probably thinking that beta 2, if I'm trying to put a sign on it, that the relationship between, that the relationship between income and birth weight, higher incomes likely lead to, being able to afford better health care while pregnant, better food. So it's likely that it's going to have a positive effect on the child, thinking about positive birth weights, or higher birth weights representing usually a kind of better outcome, okay? Or better birth outcomes. I then think about this second component, this covariance between the variable x1 I included and the second variable, x2, which I didn't include in the regression. Well, what do you think the relationship is between mother's age and income? As I get older, I'm likely to kind of work my way up. It's likely that that is also going to be positive. Okay? Now, the variance here, we never really have to worry about because the variance of any variable is positive, right? So we can think about every single one of these three components that we have that make up the bias, right, are all positive values. So our bias, right, we can think about if we're labeling this, is going to have a positive times a positive divided by a positive. It'll be a positive amount. So when we think about what we were actually observing, that coefficient estimate of 3.5, it was going to have the true relationship plus an additional positive amount. So the actual relationship is going to be something smaller, right? Because we have this positive bias. So I kind of, and I've said this in words, I would want to justify why I thought these were true. So here it was likely that higher incomes led to better pregnancy. Here we go. To better healthcare and improved birth outcome, so higher birth weight. Justification we had here was income likely increases with age, and then we don't really need a justification for the variance. The variance is always positive. Right? So if we kind of put these all lined up here. Oops. Oh, come on. All right. So bias is overall positive because we have a positive times a positive times a positive, right? So we think that our estimate is likely going to be too high, right, with this additional positive bias. Any questions on that? This could look like a very real open-ended question that you would have to answer. No questions on that? Okay. Now, let's assume that for some reason, right, I had made the, this is the more likely correct assumption, but it's okay. Let's just assume that I said, well, I think that the effect that higher incomes would have on birth weight is actually negative. So maybe that, I don't know what your justification would be, but maybe at higher incomes, you think, I don't know, higher incomes may be more likely to have a C-section or something that is, so the length of pregnancy is shorter, and so maybe maybe that's your justification. I don't really know if that's true, but let's just assume that that's what you justified. That's okay, right? I'm not asking you to be an expert on birth weights. I'm just asking you kind of what you think that relationship is. Well, if you think it's negative, now you've got a negative times a positive divided by a positive. You would think that the overall bias was actually negative, right? And that the estimate you were seeing was actually too low because you were having this kind of negative bias pulling down the actual estimate you were able to observe. Okay, so this is an example. It doesn't matter if your assumption here is right or wrong, as long as you give me your assumption and some a little blurb of why you think that. That's okay. Okay. Any other questions on that one? Okay. I'm going to skip kind of these for right now. If we have time, we'll come back to them. Actually, I don't even know if I'll come back to them. There's other stuff we could do that's probably going to benefit you more on the exam. So let's say we start on 17, right? So let's say we've got, and this is something I think we kind of played around with this data set in class, that I've got revenue kind of for a football program measured in dollars at a university, and then I've got the enrollment of the university as well. And here I've got male enrollment. So what would I expect the sign and the size of beta 1 to be? Well, if I'm thinking about the slope coefficient, it's the effect of one more student on football revenue. So if I have one more male student, how much do I expect football revenue to go up? Now here, size is a little bit ambiguous, right? But if you're thinking about magnitude of this estimate, I'm thinking that, if it's just one more student, I would likely not expect it to have a very large impact on football revenues. Now, when I say not a very large impact, that's relatively, I'm thinking about football revenues are in the tens of hundreds of millions. And so one more male student, I wouldn't expect it to increase it by, say, I don't know, $3 million or anything. Right? So I'm thinking the size is likely going to be pretty small. And I'm also thinking about if I have more students, well, there's just more students to actually attend the games. And so maybe, ticket sales go up. The more students I have, the larger my university, more resources my university is going to have to attract maybe better quality athletes. And so I'm probably thinking that the sign here is going to be positive. It's probably hard to find a story as to why having a higher male enrollment is going to have a negative impact on your football revenues. So I go down here and look at the output, and sure enough, it looks like it's a positive amount. So it's about $2,000, which might not seem very small, but when we're thinking about the relative size to kind of what the overall football revenues could be, you know, $2,000 isn't that great. Not a very large effect. I kind of already mentioned what the interpretation would be, but now that we actually have a coefficient, we can kind of write this out. So just to kind of review, right, the general interpretation is a 1 unit, increase in our x variable causes the predicted y value to increase, or if it's negative, decrease by whatever that coefficient value is. So for us, our x variable is male enrollment. So what's the units? Well, one more male student, that would be a 1 unit increase, would predict that the y variable, which here is football revenues, would increase by, and our coefficient estimate is 2,621 and dollars, right? So here's kind of our general interpretation, and then we'll just write it out in the context of our example. Okay. Any questions on that? Okay. What is the test statistic for the intercept here? Well, I show you the test statistic, but let's just assume that on the exam, I somehow, you know, put in a text box to blank this out. How did Excel come up with that test statistic of -17? Well, anytime we want to find a test statistic, it's simply, for a coefficient, it's simply that coefficient divided by the standard error. So here, if we took, what, 2,569,601, divided it by 147,466, we would end up with that -17. Right? So let me see if I can get this in here. So we would just take our test statistic would be equal to $2,569,601 divided by 147,466. Right? So just divide that coefficient by that standard error. Okay. We could do the same thing for this test statistic on male enrollment. You would just take the male enrollment coefficient and divide it by the male enrollment standard error. Okay. So those test statistic questions should be pretty easy. I mean, it's a pretty easy thing, I think, to calculate those test statistics. The next question, well, before we get to it, one other thing just to review. Notice these are very significant. They both basically have p-values of 0, and so we would reject the null for both of the intercept and male enrollment. Remember, the null, right, our null hypothesis is always that slope coefficient, I apologize. That slope coefficient is, why is this going on? Okay, so that slope coefficient is equal to 0. So we can reject that. So we can reject that there's no relationship between male enrollment and football revenues, or we found strong evidence that there is a relationship. Okay. So the next one is, suppose we include a squared term on male enrollment. What would you expect the sign of the coefficient to be? I think I put in here basketball. I apologize for that. I get mixed my sports up. All right. Draw out that relationship after you say what you expect the sign of that squared term to be. So before, this was the equation that we were running. So now we're going to be thinking about, copy this down so we can have everything together here. Now we're thinking about what we want to do is include this additional term that's going to have its own coefficient. It's going to be male enrollment. Get out of the way, zoom. Male enrollment squared. Okay. So, you know, here, you know, once again, there's not necessarily, if you can justify either one, that's fine. So here we're really thinking about, we have a nonlinear effect, right? So when I'm thinking about the relationship between enrollment, male enrollment specifically, and kind of football revenues. So here we had male enrollment, right? Here we've got kind of revenues, okay? So I'm thinking that the relationship might not be linear, that the very first dollar, the very first male student enrolled might have a larger increase or a smaller decrease than one more male student enrolled after I've already got 3,000. Right? So my expectation would be that as we get higher and higher enrollment, right, eventually it's to a point where, well, if my male enrollment is more than the number of seats that are available at the game, I'm not getting any additional ticket revenue for sure, right? And so maybe it's that initially there's these very large effects, but eventually one unit increases aren't going to have a very strong effect at all. Okay? If I have something that's increasing but at a decreasing rate, right, eventually one unit changes start to produce almost, right, no change in y, then that's where we would think that that first coefficient was greater than 0, and the coefficient on the squared term, right, it's at a decreasing rate, oops, sorry, at a decreasing rate, so negative here for that second coefficient on the quadratic term. Okay? So here would be me kind of drawing out what I think that nonlinear relationship is, and then kind of explaining what I think the signs were. Now, if I thought for instead, I said, well, initially, I don't think that one more student might not be able to, there won't be a very large university, there won't be a lot of buzz around the football team, so I think that actually the effect initially might be really small, and then eventually as I get to higher and higher numbers, well, now I'm really building this like massive kind of fan base, and maybe the team gets better, and so that I can, get people to spend more money on apparel and tickets. If that's the case, I still think there's a positive relationship, but I would think that it's increasing at an increasing rate. So there I would think that the second coefficient is positive. Okay. Any questions on that one? And there what I kind of want you to do is just like I did, label your X and Y axis, kind of draw this nonlinear relationship, and then based off of that, kind of justify why you would expect this sign of beta 2 or kind of B2 as I was writing on the board, which is, there's no difference between that's just really just notation. I could write this out and just call this, I just do it usually for simplicity when I'm writing it out, A, B1, and B2. Okay. It's the same thing, just a little bit different notation. Any questions on that one? Okay. So now let's assume that we don't include this quadratic term, but we do include female enrollment and men's basketball revenue. Right? So, let's say we run the following regression. I'm going to hit enter here a few times so I can get this all to be on the same page. Maybe. There we go. And this is the output that I get from Excel once I include those additional terms. So this is one question that I didn't realize was on the practice exam that I wanted to make sure we got to today, because I'm not going to expect you to find p-values. Okay? So I will never do something like this. I could blank out the test statistics and ask you to find those, but for the p-values, we'd have to start talking about things like degrees of freedom, which we just didn't really get into with linear regression. So a question like 21, if you're kind of going through and studying, you won't have to ever answer one that's like that. Okay? Now, if I show you the p-values, I guess you could answer that, right? Like, the p-value for female enrollment here is 0.23. Getting all kinds of interruptions today. So, suppose Lapua, get over here. Apologize for that. So suppose we want to test for whether the additional two variables that we included are jointly significant. Hey, you made so much noise. So here, let's see if we can get you a, hey, come here. You want to make an appearance? No? Come here. Okay, well, never mind. Now, let's see if we can get, he's not cooperating, so. Okay, now we got his screen time. Hopefully he'll be happy. So, now that we've included these additional two variables, right? We could test for something called joint significance, right? So this is once again another question I wouldn't ask you, but I would replace this question with something like this. How much more of the variation in football revenues can we explain with the added independent variables? Okay, so I'll update kind of the this final practice exam to get rid of those questions and add this one in. When I originally uploaded this, I thought we were going to maybe go through some of that new stuff last week. I just decided that not to throw more information at you. So really all I'm focusing on here is how much more of the variation could I explain? Well, when we're talking about how much variation that we're explaining of the y variable, we're really thinking about the r squared. So if I look at this r squared, it's 0.63. So my new r squared is 0.63. If I go back to my original output, when I only included male enrollment, my r squared was 0.59. So it's as simple as looking at the new r squared after I added in these additional independent variables, looking at the old r squared that left them out, and then kind of what's the difference between the two. So we've got what? 0.14. So the proportion of the variation, the additional proportion I'm explaining is 0.41, or I'm explaining about 14% more of the variation in football revenues by including these additional control variables. Okay? Any questions? I know I kind of jumped around a little bit and we had a little bit of interruption there, but hopefully we kind of got a little bit out of that discussion in terms of thinking about how we think about r squareds and compare r squareds across different regressions. Any questions on that? We'll wait here. And I believe we went through these, or we went through 23 last class. So then we'll come down here, the last set of questions. Let's assume that I ran the following regression, right? So I got the log of weight, and I'm just running a pretty simple regression with one independent variable, which is the natural log of height. Okay. So I run this regression. Here's my output. How do I interpret beta 1 here? So this is a discussion. If we go back, we had, I think, 2 different lectures I kind of mentioned. One time I went through the board, though, and kind of laid it all out, right? So I do that here. I'll do that here again in just a second. Another good review is going to be looking at the individual assignment number 3 answer key I put up. It's a different data set than you would have worked with on yours, but it gives you kind of what your answers should have been and a little bit more explanation as to why they should have been what they are. But if we have this regression, right, anytime we have a log-log model, everything is percentages. Okay? So I saw some confusion that with some emails and things. It's not a 1% increase in the natural log of height. You literally can interpret this as a 1% increase in height would predict that the y variable goes up by 1.3%. So if height goes up by 1%, we would predict weight goes up by 1.3%. So kind of the general interpretation would be a 1% increase in x causes the predicted y value to increase, or if it's negative, decrease by I'll call this here. I just want to copy this so I don't have to, whatever that coefficient is, percent. So for us, that was a 1% increase in height caused the predicted weight to increase by 1.3%. Okay. So the way that we know it's a 1% increase is when we take the natural log, that automatically we can start thinking about that variable. Changes in that variable will now be percentages. So if I have the natural log of height here, any unit changes I'm thinking about, there aren't unit changes anymore. The only changes that I'm observing are now percent changes. And then that's why the coefficient also has a percent change on the y variable, because we're taking the natural log of that as well. Okay, get the question, okay. Interpret the r squared and talk about one way we could increase it. So our r squared here is 0.048. So we were only explaining 4.8% of the variation in weight. Right? So it's not just in the natural log weight, it's in whatever that underlying variable is weight. Right? So there's really two things that we've talked about, really only two things that, well, I guess I'll go with three. There's really only three things we've talked about that we could do to increase the R squared. One, include additional control variables, right? Maybe include gender here. Two, we could change the model. So instead of using a log, we could use a level model or a log level model. And the third thing, which kind of is like including an additional control variable, but what we could do is not just look at height. Maybe if this was even like a level model, maybe include a quadratic term of height, right? So we'd have height and height squared, okay? Those are really the three things that we've talked about that can increase that R squared, potentially, right? Potentially this is the best model. Maybe we run the level model and it actually has a lower R squared, but that's one potential thing that we could do to increase the R squared. Any questions on that one? Okay, so that gets us kind of a pretty good amount through. Like I said, I'm gonna not go over, I forget what questions it was now, but you have the answer key. Which ones didn't I go through? Here, these 14 through 16. But you have the answer key. I got some other stuff I think will be more beneficial that we'll go over right now. So I put up some additional questions called final exam extra practice. This is under the final exam practice materials folder. I think what I want to do is save this for Friday, and I'm going to actually walk us through a little bit of that individual assignment answer key, okay? So this is going to kind of keep with our log level discussion. So question one was some ANOVA stuff, so I'm not going to go over that. But question 2 and 3 dealt with linear regression. Here, the one example I use is I had total points scored in a football game and then kind of weather. So the reason why I had this data set laying around is I was actually thinking about how can I maybe use weather, upcoming weather to kind of predict total points of a football game, because you can bet on the over-under and make a bunch of money, but you probably don't care about the motivation. So here I've got the temperature, and here I've got the total points scored in a football game. Thinking about maybe colder games, it's more difficult for teams to score points. Right? I also took kind of the natural log of those two variables, so I could run my different log level, log, and then here I had my level output as well. So the level output, hopefully we're pretty okay with, right? This is going to be that the interpretation on my coefficient is for every 1 unit increase in my x variable, the predicted y variable will go up by whatever that coefficient is. We've already talked about that today, right? So a 1 unit increase in temperature would be 1 degree hotter, would predict the total points scored in the game goes up by 0.048. So for every additional degree warmer, expected points go by 0.048. So I'm going to start building kind of something, and I'll kind of write this out, and as you're going through, it might be a good idea to write this down before you go to the exam. So we've got 4 different models that we are going to be thinking about. So here I've got, first one is level, right? So we're thinking about this is a 1 unit change in x. So kind of think about maybe what's the change in x here. So 1 unit increase has an effect of, what's the effect that it has on the predicted y? Just kind of beta here, right? So that's going to be our first line, right? Level models we interpret as a 1 unit change in x predicts that the y variable changes by just beta, right? That's easy enough, right? Beta units. Oh, the third thing we could do to increase the R squared was include the quadratic term. So that was like when we had just male enrollment on the previous example, we could include male enrollment squared. I'm assuming that's what you're referring to. Okay, hopefully, if not, let me know. So that was the first one. I think that's a fairly easy model. The next one that we have is the log. And we just kind of talked about that one. So there, I had my y variable. Get zoom in on this. My y and my x variable, I took the natural log of both, right? So now the interpretation is that a 1% increase would predict, a 1% increase in temperature would predict that the total points scored increases by 0.06%. So now what we're thinking about is we've got a log-log model is a 1% change in X causes my predicted Y value to change by beta percent. So it's 1% change in X causes Y to change by beta percent. So that one I also think is relatively easy. The next one we have is this log level. So the way that when I'm saying log, level, the first word is the Y variable, the second word is the X. Then that kind of, falls in line with how we would write out the equation. So in this output, it's a log level. So I took the log of the Y variable and I didn't do anything to that X variable. Right? So here I've got this coefficient estimate of 0.0015. Right? So the interpretation here is if temperature, right, I didn't take the natural log of it. So if it goes up by 1 unit or 1 degree, the predicted Y value changes by this coefficient, right, times 100 to get it into terms of percent. Okay? So here we've got a log level model. It's a 1 unit change in X causes the predicted Y value to change by beta times 100%. Right? So 1 unit change in X causes Y to go up or down by beta times 100%. Okay? So in ours, it was a 1 unit change was 1 degree higher, predicts that total points scored goes up by 0.0015 times 100, so 0.15%. So here, kind of the effect was, oops, I forgot my equal sign. Okay, so 1 unit change in X causes Y to go up by 0.15% here. If I then look at my level log model, well, remember, the first word is the Y variable, so level, so I didn't do anything to the Y variable, but I took the natural log of my X variable. So now, because I took the natural log of the X variable, it's a 1% change in temperature, causes the predicted Y value to change by the coefficient divided by 100 units. So here we've got our final kind of level log. It's a 1% increase in X. Causes Y to change by beta divided by 100 units. Okay. So there, the coefficient we had was about 2. So 2 divided by 100 is 0.02. So a 1% change in temperature would predict that the total point scored goes up by 0.02. Okay. So here, right, we would take 2.04 divided by 100. So a 1% change in temperature causes the predicted points to change by 0.02 units, right? So just points. Okay. And I have these kind of written out in words on this question 3. So this is what we just said. If you kind of want a review of kind of my words there, but I think that table that I kind of drew out, I think this is really important to kind of keep it all straight, right? I'm not restricting what you have in front of you on your exam. If you're writing things down like on a sheet of paper, I would suggest having like a little table that looks like this. I just think it's a nice way to kind of keep it all straight. Right? I know I did that in class one day, but just kind of reviewing that again. I also talked about kind of here on this, one of the questions on the individual assignment was which one's the best model. You just have to go through, basically all I would expect you to do is look at the R squared. So 0.002 on that model, 0.0036, 0.0033, 0.0027. So that log level had the highest R squared. Now, clearly my regression here is not great. I don't have any other control variables. I'm not explaining a lot about, a lot of the variation in my Y variable. But I thought this is a, wanted to walk through this answer key in case, you know, even if you got a good grade on it, you might not have looked at this. This is still a good study tool, okay? Because I kind of walked through a completely different example from what yours would have been. So it just gives you more practice with it. Okay? Any questions on that for you? I think I might just have a quick kind of, unless there's specific questions. Like I said, those other questions we didn't cover on the final exam practice, well, not this one, final practice exam, I think are relatively easy. It's really just other stuff that we've talked about today, calculating test statistics, interpreting coefficients, and interpreting intercepts. So a little bit more practice with that. So maybe do these on your own and see if you can reproduce the answers that you see in the answer key. And then on Friday, I'm going to go through these questions and an Excel file that has some of their output. So I think that'll be important. The one thing that we haven't covered a lot of in the review is how we interpret multiple dummy variables. So we'll get an additional kind of review of that on Friday, but I know that discussion will take a little bit longer than 10 minutes. I want to spend a little more time on that. So I'm going to save that. And then also we'll kind of review another quadratic example. We'll save that for Friday. So are there any other specific questions, any problems that you're working through? Anything related to the individual assignment? And just a quick poll, since those of you who are here. Like I said, I know for sure we need to go through an example where we have multiple dummy variables. I want to do a review of that. So we'll do that on Friday for sure. But is there any other examples you would specifically want to see? So kind of what I'm thinking about here is, you know, what are you having kind of the most difficulty understanding? Is it, you know, do you want to see another one of these quadratic examples? Kind of have one ready to go. Determining significance, interpretation of coefficients, additional log-log stuff. Is there anything specifically that any of you can kind of think about you'd want to see again? Or just kind of leave it up to me? Significance levels. All right, yeah, we'll do some review of that here and kind of looking at output, being asked to identify kind of the significance of different variables. So we'll make sure we definitely hammer that and review that on Friday as well. It's harder for me to gauge how the understanding that we have kind of right now with being virtual, but hopefully we're feeling kind of okay with all this linear regression stuff. I mean, I've been able, you know, it's been good that we've had a little bit extra time to go through a lot of examples. I know that it's kind of difficult, it's kind of new, but hopefully we're starting to get, you know, kind of feel a little bit comfortable going into that final. You know, really the beginning of it's going to be a couple of questions on that matched pairs and some old hypothesis testing stuff, a little bit of ANOVA, and then really the rest of it's going to be these, you know, interpreting regression output, calculating test statistics, you know, all the other, you know, interpreting R-squareds, things like that. When is the exam? So it'll be Monday through the end of the day on Wednesday next week. Now, Monday, I will not be doing additional review in the sense of like going through problems, but I will kind of sign on right at 1. And if you have last minute questions before you take the exam or you want, I'll be here almost like in using it as an office hour, like an hour, you know, office hours. But try to get there really close to 1. You know, if the first 10 minutes go by and nobody's kind of showed up, unless you've emailed me ahead of time, I probably will just kind of close that Zoom. But I will be here on Monday at 1 if you want to come with any questions. But I won't be like coming in with material to go over. Any other questions for me before we? Like I said, I'll be getting those individual assignments graded as well. More correlation examples. Oh yeah, the bias. Yeah, I can yeah, I can do that. I can I might re-upload this Excel file then and build in one more example like that where we have an omitted variable bias and think about the correlation of the variable left out. I assume that's what you were kind of referring to. Okay. Any other questions? All right, so yeah, I think we'll have a good amount to go through with this. We'll be looking at that GPA data set again, but I've structured a little bit differently so we can get some more out of it than we have in previous talks, and then we'll cover that on Friday, and that should be hopefully get us ready for the final. The other thing I wanted to mention before we get out of here today, if you could do me a favor, I get inundated with the emails. I'm sure you are too. But if you get 5 minutes to go on and fill out those teacher evaluations, I greatly appreciate it. Helps me out, helps the department, the university, the college out. So I know I hate getting the emails. I don't know if you guys get as many as I do, but it's if you could do that, I would appreciate it. So if there's no more questions, we'll do one last review on Friday. I'll be available for office hours on Monday, and then we've got that exam next week. So good luck with your studying, and I will see you on Friday.